All right, let's get started. I want to have a quick review. What did we do on Monday? This week is a week of energy balances, which is nothing but balancing your bank account, but in units of energy instead of units of money. The first concept we used was control volume. And control volume, all it is this dash dot blob, right? But it's extremely important because it separates inside from outside the world. And then we can talk about flows of energy, flows of mass. And everything else we're going to be doing in the class builds on this concept. So what is associated with this potato here, right? What is associated with the potato is the energy balance. So there are two types of people in this class. Those who know what to do and will write the energy balance. And those who don't know what to do, those should write the energy balance. So we are all the same. If you don't know what to do, you write an energy balance. And the energy balance always goes together with a control volume. Because you cannot talk about an energy balance without saying a balance of what, right? So these two things, which, by the way, I often forget myself, but these two things, believe me, by the time I think I was so fast doing things without my control volume, I realized I should have done it to know what I'm talking about. Always together. Anybody cares to remind me of what the energy balance was? Q in, minus Q out, Q generation. What is QST? Stored. All right. Units of Q. The units of Q are joules. Right? And somebody asked me too, is thermal energy the same as enthalpy? Yes, that's exactly true. So heat transfer is a fairly good field, but it suffers from a problem of many other fields of engineering too. Sometimes we have different words for the same concept. I know it seems like as if it was designed to confuse, right? But enthalpy, thermal energy, same thing. Q stored, we said, is mass time the enthalpy, right? And the enthalpy here that has an arbitrary reference. How does this curve go? If it is water and we start, let's say, at minus 20. How does the curve go? Goes up, and then? Yeah. And then? Yeah, right. And this would be 0 degrees C. And something I mentioned to you that is super important in your life as engineers. And for the exam, you're always assuming something. Whether you're aware or not, you're always assuming something. So if we say that water freezes at 0 degrees, although it seems natural, we're assuming this is at 1 atmosphere, right? So 0 degrees here, 100 degrees for evaporation, right? What is this, the height of this jump? Has a name, right? Latent heat, right? Which we call here, using the box notation that I despise. But anyway, ISF, this is IFG, this is a latent heat of vaporization. What is this slope? Yeah, heat capacity, specific heat, right? C of the solid, C of the liquid, C of the gas, right? And we're assuming it's always a constant pressure in our problems. Okay, so this is pretty good. Something that is a coincidence, but an amazing coincidence, is that the slope is more or less constant. If this is more or less like a straight line, what does it say about the specific heat? It's constant, right? Right? And didn't need to be that way, but it is that way. It's amazing. Now, in reality, it's not a straight line, but it's so close to a straight line that we are not going to care much. But for things like water or air or a bunch of other stuff, the book has the specific heat as a function of temperature. And in that case, if you want to calculate enthalpies, you need to do an integral. And there is a problem we have in these nodes about calculating the integral to get an enthalpy out of a specific heat that is variable.